Hi guys, in this lecture what we will do is, we will take a look at some of the problems based on synchronous machine in order to understand what kind of questions can be asked in GATE examination from this chapter. So the first type of problem that can be asked is based on induced EMF. Now in synchronous machine, induced EMF is given by 4.44 Fn phi kW. Kw is the winding factor, which is basically product of pitch factor and distribution factor. Pitch factor is given as cos of epsilon by 2, whereas where epsilon is short pitching angle. Okay, and Kd is given by sine of m beta by 2 divided by m sine beta by 2. Here m is slots per pole per phase and beta is 180 upon slots per pole. Okay, and here n is the number of turns per phase, f is the frequency, phi is the flux per pole. So that is how we calculate the EMF. And when we talk about three-phase, in three-phase alternator, in case of star connection, you have to remember line voltage is root 3 times phase voltage. Also, you have to remember that third harmonic is absent from line voltage. Okay, it will get cancelled out in line voltage, but it can be present in phase voltage. Whereas in delta connection, line voltage is equal to phase voltage, so third harmonic can be present in line as well as the phase voltage. Now let us understand the question that is given to you. The phase EMF of a 3-phase 50 Hz alternator consists of a fundamental, 20% third harmonic and 10% fifth harmonic. The maximum amplitude of fundamental is 1000 volt. We need to calculate RMS line voltage when the windings are in star and delta. So the first thing that you need to carefully consider is RMS line voltage, whereas the voltage given is amplitude. That means in the last step of the problem, you have to remember to divide it by root 2 in order to convert it to a sinusoidal RMS value. Now let us see, fundamental is given to me as 1000. Third harmonic is 20%, so third harmonic will be 200. Fifth harmonic is 10%, so it will be 100. Now we know in star connection, in line voltage, third harmonic will not be present. Line voltage will be equal to root 3 times phase voltage. How to calculate phase voltage? Using fundamental and fifth harmonic. Why not third? Because in line voltage, third harmonic will not be present. So how much will it come out to be? 1740.689. But remember, this is amplitude. So the RMS value will be 1740.689 divided by under root of 2, which will turn it to 1230.85 volt. Now let us consider the case when we have delta connection. In delta connection, line is same as phase, so that means third harmonic will also be present, which means RMS value will be 1000 square plus 200 square plus 100 square under root. So this will come out to be 1024.69 volt. Now if it is the case, what will be RMS value? RMS value will be this value divided by root 2, which comes out to be 724.568 volt. Okay, and remember how I am using this formula. This formula is entirely based on Fourier series computation, which states that if you want to add different frequency components, you can add under root a square plus b square plus c square, as all the components are orthogonal to each other. Moving forward to the next problem, it is saying calculate the phase and the line voltage of a three-phase star-connected alternator with uniformly distributed winding. Now this term is pretty important to us. As I told you, KD is sine m beta by 2 by m sine beta by 2. Winding is uniformly distributed if beta is very small. If beta is small, sine of beta by 2 can be replaced by beta by 2. So it becomes like this. This term m beta is also called as phase spread. Okay. Now what it is telling us here? It has T full pitch turns. So number of turns is T. Induced EMF in each turn is EM. That is also peak value. We have to find out phase and line voltage when each phase has a phase spread of 2/3 the pole pitch. Now what is pole pitch? Remember, it is always 180-degree electrical. It is basically electrical angular separation between two opposite poles, that is north and the south pole, which means phase spread is 2/3 of this. So it will be 120-degree electrical. Okay, and this pole pitch is universal, it is always 180-degree. So what will be KD? Sine 120 by 2. Remember, in the denominator, this angle should be in the radians. So 120 by 2 is 60-degree, or we can say pi by 3. So it will come out to be 0.827. Now, as I have already told you, the expression for induced EMF, what will be my induced EMF? 4.44 F N phi kW. Now it is saying full pitch, which means Kp is 1. But in this problem, it has given me induced voltage in each turn. So I need not apply this formula. What I will do, number of turns per phase are T by 3, because T are the total turns. We have 3 phases. Induced EMF in each turn is EM. In order to make it RMS, EM by root 2 into kW, which will essentially be KD, because Kp is 1. So it will come out to be 0.195 EM. What about line voltage? Multiplied by root 3, because it is star connected. So this will turn out to be 0.3376 EM. So that is how you can calculate the induced EMF in any alternator when you are already aware about the winding orientation. Next problem, let us see on the similar concept. It is saying we have a 16 pole alternator, that is poles are 16, slots are 144, conductors are 10 conductor per slot. Now flux per pole is 0.03 Weber. Speed is 375 RPM. We need to calculate the frequency and the phase and the line voltage. Now as you see here, what happens is, basically, you know the speed. We know synchronous speed in any machine is 120 F by P, which means 375 is equal to 120 into frequency is unknown, but we have 16 poles. So frequency comes out to be 50 Hertz. Now first calculate beta. As I told you, beta is 180 upon slots per pole. Poles are 16, so it will be 20-degree. What about M? Slots per pole per phase. We have 3 phases. Poles are 16. It will be 3. We can calculate KD. sine of 3 into 20 by 2 by 3 sine 20 by 2. It will come out to be 0.9598 or approximately 0.96. Now calculating EMF is pretty straightforward. How? EMF is 4.44. Frequency we just now calculated 50. Now number of turns. We have 144 slots. We have 10 conductors per slot, which means number of turns will be divided by 2, because in each turn there are 2 conductors. But that is total number of turns. We need number of turns in each phase, so divide it by 3. This is your number of turns per phase. Phi, it is given as 0.03 Weber. Then Kw, which is essentially Kd, since nothing is said about the short pitching, Kp can be taken as 1. So that is how you can calculate your EMF. So basically 4.44 into 50, it will be how much? 220 into 240 into 0.03 into 0.96. Similarly, if you wish to calculate line voltage, it will simply be root 3 times phase voltage, because it is star connected. Is it fine? So that is how you can tackle the problems based on winding factor, winding distribution factor, and the pitch factor. Okay, that is the first category that can be asked. In a similar way, I can ask you problem based on design of the winding, not essentially its parameter. So let us see here. A 4-pole 3-phase double layer winding is housed in a 36 slot stator with 60-degree phase spread. Coil span is 7 slot pitches, number of slots in which top and bottom layer belong to different phases. Okay. Now see, slots are 36. What about slots per pole? They are 9. Now how poles are arranged? North, south, north, south. And each pole will have like this 3, 3, 6 and 3, 9. Each will have like this 9 slots. Okay. Now what is meant by a double layer winding? A double layer winding essentially means that in each slot you have 2 coil sides. One coil side belongs to one coil and the other one belongs to a different coil. Now what is slots per pole per phase? That is 9 by 3, that is 3. Which means out of 9 slots under each pole, 3 slots are given to a single phase. So let me show you how we can design the winding. Suppose the first 3 slots are given for A1, A2, A3. Then B1, B2, B3. Then C1, C2, C3. Okay. Now it is saying that the coil span is 7 slot pitch, which means if one side of the coil lies in first slot, the other one will lie in 1 plus 7, that is the 8th slot. So in the first one we have A1, its other side will lie in the 8th slot, that is here A1 dash. Now as you can see, in each slot we have 2 winding, and if one side is lower or it is lying downwards, the other side will lie on the upper side. Which means, see, there is one slot. In each slot you have to place 2 coils. So one will be placed downwards and one will be placed upper to that or above that. Okay. So if you are placing one coil side of a coil in a lower slot, then in the other side it should be upper slot. So that is what I have done here. Similarly, A2 is in second slot, so its other side will be in 2 plus 7, 9th slot. Here it will be in A3 dash. Here it will be B1 dash, B2 dash, B3 dash, C1 dash, C2 dash, C3 dash. Now similarly, under south pole we will have other phases like A4, A5, A6, B4, B5, B6, B7, B8, B9. Sorry, it will be C4, C5, C6. Okay. Again, 3 slots are given to each phase. And based on coil span, A4 other end will lie in the this slot A4 dash and it will be A5 dash. Now see this one. These two belong to same phase. These two belong to same phase. These two also belong to same phase. So out of 9 slots, there are 3 slots in which both the windings belong to same phase, which means 3 out of 9 have same phase. We have total of 36. So 12 out of 36 have same phase. What about different phases? It will be 24. In 36, if 12 belong to same phase, that means 24 will belong to a different phase. So that is how a double layer winding is designed in case of any machine or any rotating machine such as synchronous induction or even a DC machine. So that is the basic concept of a double layer winding. Next concept, let us move on to synchronous impedance. See, in synchronous machine there are many methods which are used for finding the voltage regulation, such as EMF method, such as MMF method, such as Portier triangle method, and then there is American Standard Association method. But in this EMF method is most important pertaining to previous year gate questions which have been asked, because it helps you to find the synchronous impedance, which later on helps us to find the voltage regulation. So from gate point of view, this method is most important, others are not that significant. So what happens is, we perform an open circuit test which gives us the value of induced EMF. Then we perform a short circuit test which gives us a value of the short circuit current. So in a 3-phase machine, synchronous impedance is nothing but open circuit voltage by root 3 by short circuit current. That is for basically star connection. Is it fine? Because we want to take phase voltage. Remember, these both two should be at the rated field current. They must be at the same field current. Now, in order to find out resistance of the winding, we perform a DC voltmeter ammeter test. In this, if the winding is star, then per phase resistance is measured resistance by 2. Whereas if winding is delta, per phase resistance is 3 by 2 times the measured resistance. This also you have to remember, that we construct or we perform a DC test in order to find the winding resistance. Now let us see the problem that has been asked. The resistance that is measured between two terminals of a star connected alternator is 1 ohm, which means per phase resistance is 1 by 2, or we can say 0.5 ohm. Okay, because it is star connected. Now it is saying on short circuit field current of 40 ampere gives full load current of 20 ampere, which means short circuit current I know 200 ampere. The line voltage on open circuit with same field excitation is 2010 volt, which means EOC is 2010 volt, and it has given us same field current, which means we need not change the value of field current. So if you want to find out synchronous impedance, it will be open circuit voltage by root 3 divided by short circuit current. So how much will this come out to be? 5.802 ohm. What about synchronous reactance? We know impedance is composed of reactance and resistance, so it will be Zs square minus Ra square under root 5.802 square minus 0.5 square, which will come out to be 5.78 ohms. Okay. So that is how you can calculate the synchronous reactance. Next, let us consider another problem based on synchronous reactance. It is saying a 100 kVA 415 volt line voltage star connected synchronous machine generates a rated open circuit voltage of 415 volt. So EOC is 415 volt at a field current of 15 ampere. The short circuit armature current at a field current of 10 ampere is rated armature current. So IA rated, but it is at a field current of 10 ampere. So I cannot directly use the value of EOC and ISC. Why? Because they are at different field current. So what I'll do here is I will calculate short circuit ratio. What it is? It is the value of IF to generate rated open circuit voltage divided by IF to generate rated short circuit current. Okay. So how much will it be? 15 upon 10, that is 1.5. That is called as short circuit ratio, and it is equal to 1 upon synchronous reactance in per unit. These two relations are pretty important, which means synchronous reactance in PU is 1 upon 1.5, or we can say 2 by 3.667 PU. Okay. Other way around, what you can do is you can first find out IA rated. How you can find out IA rated? That is power upon root 3 into line voltage. Once you have IA rated, we know that the short circuit characteristic of an alternator are linear. So what I'll do is, suppose IA is X at 10 ampere field current. So IA will be sub 1.5x at 15 ampere. Why? Because if field current becomes 1.5 times, IA will also become 1.5 times. That is due to linear short circuit characteristic. Now we have EOC, we have IA both at 15 ampere field current. We can calculate excess, but it will give excess in ohms, which you then have to convert in PU. Is it fine? So it will be a bit more lengthy method as compared to this one using the short circuit ratio. But in case in exam you get confused about SCR, so better to use the conventional method. The next type of problems in synchronous machine are based on power angle equation in case of a cylindrical rotor. So what is the power equation? Power is EF Vt by Zs cos of theta minus delta minus Vt square by Zs cos of theta. Is it fine? So what is Zs? Zs is Ra plus j-axis. It is equal to mod Zs angle theta. So theta is the impedance angle. Delta is basically your power angle. EF is induced EMF. Vt is the terminal voltage. Now in this equation, if you put all the voltages in terms of phase voltage, what you will get is per phase power. If both the voltages are line to line, you will get the three phase power. So remember, if these are line voltages, power will directly be three phase. If you want to find out reactive power, just replace cos by sine in this expression and you will get the reactive power. This same equation becomes EF Vt by Xs sine delta in case you neglect Ra. Okay. If Ra is 0, this will become this. And what about reactive power then? In that case, reactive power would be Vt by Xs EF cos delta minus Vt. So that will be your reactive power. Now let us proceed with the problem that is given to us. In this problem, it is saying a three-phase star-connected alternator is delivering 20 megawatt and 8 MVAR, which means S is 20 plus J8 MVA. Terminal voltage is also given to us 11 kV. Now alternator has synchronous impedance of 0 plus J3 ohm, which means RA is 0, XS is 3 ohm. We have to determine the load angle and excitation EMF. Now there are two ways to approach this problem. Either you can use the equations for P and Q, and there we will have two variables EF and delta. We will have two equations, one for P and one for Q. Solve two equations in two variables in order to determine EF and delta. Or other way around, what I can do is, I know S is equal to root 3 VL IL conjugate. Now it is a star connected alternator, which means IL is equal to I phase. From here I can directly calculate IL S conjugate by root 3 VL conjugate. So it will be 20 minus J8. VL is given to me as 11 kV. So it does not get affected by conjugate. Why? Because I am assuming VL as reference, which means it is 11 angle 0 kV. So conjugate shall remain same. So it comes out to be 1.13 angle minus 21.8 degree kiloampere. Once I have the value of IL, I can calculate EMF by the KVL, which means 11,000 by root 3 plus J3, that is XS, into 1.13 angle minus 21.8 into 10 to the power 3. So it will be 8.23 at an angle 22.47 degree kV. That will be your induced EMF per phase. If you want to convert it to line, multiply it by root 3, and this 22.47 is your delta, that is the load angle, or it can be called as the power angle. So this way I have saved a lot of steps, but here it requires phasor calculation. If you don't want to go into phasor, use individual equations for P and Q. Next question based on same concept is, a turbo alternator having a reactance of 10 ohm has armature current of 200 ampere at unity power factor when running on 11,000 volt constant frequency bus bar, which means terminal voltage is 11 kV, IA is 200 ampere at unity power factor. Now if prime mover input is not changed, which means real power is constant, EMF is raised by 20%. So now first thing that you need to remember is, in synchronous machine, no matter what changes you make, you can never assume delta to be constant. Okay? Either you can assume power to be constant, real power, or you can assume excitation EMF to be constant but not delta. Delta can never be taken as constant. Okay? So here real power is constant. So first let us find out the value of EMF. EMF will be 11,000 by root 3 because it is star connected. Even if it is not mentioned it is star connected, by default it is star. If it is given as delta, keep this in mind that you do not have to divide by root 3. That is a very common mistake that you can commit. Then unity power factor means angle of 0 into reactance is 10 ohm. Resistance is not given, so we are neglecting it. This comes out to be 6658.328 at an angle 17.48. Now we have got delta. We know real power is EV by X sine delta. If resistance is 0, it can be taken as constant. Since it is connected to infinite bus, terminal voltage is always constant and reactance cannot be changed, which means E into sine delta is constant. If E into sine delta is constant, it means E into sine of 17.48. Now you have raised the EMF by 20%, which means it becomes 1.2 E into sine delta. So from here, if you calculate delta, it comes out to be 14.496 degree. Now we have new EMF, which is 1.2 E. We have its angle. We need to calculate armature current and power factor. One thing that we know is the terminal voltage shall remain same. So how I will calculate IA? EMF will be 1.2 into 6658, that is old EMF, 0.328. It now has an angle of 14.49. Minus terminal voltage is 11,000 by root 3 by reactance, which is J into 10. That gives us the value of armature current, which actually is equal to 243.26 at an angle minus 34.7 degree ampere. So what about power factor? Power factor is cos of voltage angle is 0, minus current angle is minus 34.7. So it comes out to be 0.822 lag. Why is it lagging? Because voltage angle is 0, whereas current angle is negative. So current is lagging behind the voltage. The next type of problem is based on basic equivalent circuit of a synchronous machine. So what is this equivalent circuit? This is our EMF. This is RA, XS, VT. This one is IA. So basically here VT is equal to E minus IA RA plus J XS. So that is the basic equation based on equivalent circuit of a cylindrical rotor machine. So here there are certain equations that you can remember. This is the basic equation based on phasor. The other equation for calculating magnitude of EMF would be V cos phi plus IARA whole square plus V sin phi plus minus IAXS square under root, plus corresponds to lagging power factor, minus corresponds to leading power factor. Okay, always remember this expression in order to find out the magnitude of EMF. Is it fine? Now let us see the problem that is given to us. It is saying a 1500 kVA 6600 three-phase star connected alternator with resistance of 0.4 ohm, reactance is 6 ohm. It delivers full load current. So let us find out full load current. 1500 into 10 to the power 3 by root 3 into 6600, because kVA is root 3 VL IL. So it will be 131.216 ampere. This is our full load current. Now based on this, we can find out EMF. What will be EMF? Terminal voltage, that is 6600 by root 3. We are dividing it by root 3 because it is star connected. Plus 131.216. It is saying 0.8 power factor lagging. Minus 36.86. What about impedance? 0.4 plus J6. This gives us magnitude of EMF to be 4366.07 volt. Now it is saying for same excitation, that is mod E in this case is constant. Excitation remaining same means field current remains same. If field current is same, the induced EMF will also be same. And same load current, which means full load current, Power factor is 0.8 leading. We need to find terminal voltage. Let terminal voltage is equal to X, let us say. We need to find this voltage. So now one thing I know is the magnitude of EMF. I am not aware about its angle, so we cannot use the phasor equation, but we are already aware about the magnitude. So I will use the magnitude equation, which says mod of EMF, which is 4.4366.07 square, shall be equal to V cos phi is 0.8 plus IARA 131.21 into 0.4 x into 0.6 minus, because it is leading power factor, 131.21 into 6 square. Okay. Now you can expand this quadratic equation. It becomes x square minus 860.77x minus 184,399.77.43. If you solve this quadratic equation, x comes out to be 4.746 kV, which means the line voltage would be root 3 times this, which is 8.22. Remember, whenever terminal voltage is asked in gate examination, if phase or line is not mentioned, by default you have to give the answer in line. Same is the case if any value is given. If a three-phase voltage is given, it is by default line if it is not specified, or if it is specified as phase, then it is phase voltage. Moving on to the last problem. Next problem is based on parallel operation. In parallel operation, what happens? We have two alternators that are basically connected in parallel. In this case, the EMF of both machines should be same. Otherwise, machine having higher EMF will cause a circulating current. Okay, because current will flow from higher to a lower voltage. So in this it is saying two identical delta connected alternators mechanically coupled to one prime mover, which means both have the same speed and same frequency, have each an armature resistance and synchronous reactance of 0.3 ohm and 4 ohm. So Ra is 0.3 ohm, synchronous reactance is 4 ohm. And they have induced EMF of 350 volt and 250 volt. Okay, per phase. Now we need to find circulating armature current. Since EMF is not equal, there will be armature current how much? Higher voltage minus lower voltage by impedance. Now if you see, this current flows through two impedances, one belonging to each machine. So net impedance will be 0.3 plus J4. So how much will it come out to be? 12.465 at an angle of minus 85.7 degree ampere. Next it asks us to find the terminal voltage. Now we know the machine having higher voltage is delivering the current to lower voltage. Okay. And so the terminal voltage will be 350 minus current. Current was how much? 12.465 angle minus 85.7 into impedance. Impedance was how much? 0.3 plus J4. So this voltage will come out to be 300 volt. Let me tell you a short trick here. This is 350, this is 250. This is basically midpoint of the circuit. These two elements are also identical. So this voltage will be average of the two, that is 300 volt. Okay, directly also you can write. The next question is output, electrical output of generating machine. Which one is generating machine? Which is delivering the current, that is having an EMF of 350 volt. So what will be output power? Output power will be 3 times phase voltage, phase current into cos of angle between them. Since 300 has an angle of 0, so it will be 85.7, same as the current angle. So this power comes out to be 840. Now remember, this is a delta connected alternator. That is why this voltage is phase voltage, or you can call it line voltage. Both will be same. Now in this case, what happens is one machine is delivering current to the other. So one is acting as a generator while the other is acting as a motor. But what happens about the losses? The losses of both the machines are supplied by the prime mover. So it is asking power of prime mover if core losses are 2 kilowatt. So we know core loss is 2 kilowatt, but what about copper loss? There are two machines. Each will have 3 resistance because they are 3 phase. So total of 6 resistance. Current is 12.465 square into resistance is 0.3. That is 6 I square R. So it is 0.28 kilowatt. So the prime mover input will be equal to losses 2.28. Here we are operating both machine at no load condition. That is why prime mover output is equal to loss. Otherwise, the prime mover output would be loss plus the output or the load power. Okay. So that will be our final answer. So these are some of the problems that can be asked in GATE examination from synchronous machine. There are some other type of problems which we shall see later.